Good morning, students. Audio video is okay. Audio video is okay.
Yes, sir.
I'm not getting your voice.
Yes, sir.
Okay, thank you.
Yes, sir.
So, in last class, we have seen how to write the general solution and some theorem related to the about the related to general solution and the particular solution. So, in continuous of that, we have this important problem. Use one or both of the methods described in section 11. Section 11 means reduction of order to find all solution of y double dash plus y dash square is equal to 0. So this is what it is, the second order differential equation. Verify that y1 is equal to 1 and y2 is equal to log x are linearly independent solution of the equation in part A on any interval to the right of the origin. Is y is equal to c1 into 1 y naught? That is the question. So here, when we solve, this by the reduction of order, because why we are applying the reduction of order? Because here y is missing as well as the x is missing. So you can solve this. So here, if you write that y dash is equal to then uh, dx will be the of py dx plus p square is equal to 0, or
Sir, your voice is breaking a lot.
okay, just wait a bit. So now please verify the audio video. Now it's okay.
Yes, sir.
So here, what I was telling, till now clear or I have to repeat? In this question, we have the second order differential equation, and it is given to you y is equal to 1, y is equal to log s are the linearly independent solution. So they are asking now, can we write the y is equal to c1 into 1 plus c2 into log x as a general solution? If not, why not? So now we have started to solve the second order differential equation. So we have the y double dash plus y dash square is equal to 0. So we have assumed that y dash is equal to p. So y double dash is equal to dp by dx. So our equation will reduce to dp by dx plus p square is equal to 0. So when we separate the variable, it will it will become dp upon p square is equal to minus of dx, and then we integrate on both sides. So it will give you minus 1 upon p is equal to x plus c, or you can say c1. So from here we can write p is equal to 1 upon x minus c1.
Sir, it will be minus x there. Sir, minus 1 upon p is equal to minus
No, it
x.
won't. It won't. It will be 1 upon p is equal to x plus c1, sir. Because it's like dp upon p square is equal to minus dx. So the minus won't be there.
Actually, here we have done mistake.
Yes.
This minus. So later on we have the means the, either you take the complete bracket or this bracket. So this will be the p is equal to minus p is equal to 1 upon x minus c1, and p is what? Divided dx. So again you separate the variable. So when we separate 1 upon x minus c1 into dx plus dy, now you integrate on both side. Integrate on both side. So left hand side will come ln of x minus c1 is equal to y plus c2. It means y will be c2 plus ln of x minus c1. So this is the solution by reduction of order. By reduction of order. Now we have to see another conceptual things here.
Sir,
Yes.
to prove it to be linearly independent, we just have to show the Ranskin.
Yes.
Okay, so that is not zero, so that is linearly independent. Just that statement.
Uh, just you wait a bit. I am telling something. Just wait a bit. Just after completion of this, if you have the doubt, then you please ask. So let now it in the B part. In the B part, verify that y1 is equal to 1 and y2 is equal to log x are linearly independent solution of the equation in part A on any interval to the right of the origin. So we take the y1 is equal to 1. So y1 dash is equal to 0. Y1 double dash is equal to 0. If you take the y2 is equal to log x, y2 dash is equal to 1 upon x, and y2 double dash will be the minus 1 upon x square. And given second order differential equation will be the y1 double dash plus y1 dash square. So when we put the value, this is the 0, this is the 0. So 0 plus 0, it will give you 0. So it y1 satisfy the given equation. Then y2 double dash is the minus 1 upon x square, and y1 dash is what? It is the 1 upon x square. So it will give you minus 1 upon x square plus 1 upon x whole square, that also give the 0. It means here you can say that y1 and y2 are solution of given equation. Let's say 1 solution of the first. And if you take the ratio y1 upon y2, so it will come 1 upon log x, not a constant. So we can say the y1 and y2 are Li solution of first. So here the y1 and y2 are Li solution. So by the theorem 15, we can write yx is equal to, or first by the theorem 14c, by theorem 14c, we can write c1 first solution plus c2 second solution will be the solution. So yx is equal to c1 y1 plus c2 y2, or c1 into 1 plus c2 into log x is right, is the solution, is the solution. Now it is not a general solution, it is not a general solution. Why not the general solution? By putting the value of the c1 and c2, by putting the value of the c1 and c2, you cannot determine this solution. Whatever the solution we have computed, right, whatever the solution we have computed here, this solution you cannot determine from there. That's why that is not a general solution. So why we are not getting the general solution? Why we are not getting the general solution? It means whatever the condition of theorem 15 that is satisfying. Then why, what is the problem? What is the problem that the conclusion of the theorem 15 is not here?
Sir, interval.
Interval, their interval is what? It is
The X
here
cannot
also we
be
have the x greater than 0. I have highlighted the equation. Anything you can recognize? There I have given you the equation of the form this. What is the difference?
it is not a standard equation.
It is the linear. Main thing is it is a linear, right? Linear second order differential equation. Theorem 15 is suitable only for the linear second order differential equation, and it is only the second order differential equation, means non-linear. It is the non-linear. So theorem 15 is true for the linear second order differential equation. So here I have concluded this: yx is not a general solution of the first, since first is not linear second order differential equation and homogeneous.
Sir,
Clear?
sir, how did you get that it's not a general solution?
Means after putting the value of the c2 or c1, can you get that value? There we have the solution c2 and log of the x minus c1. With the proper choice of the c1 and c2, can we get this solution?
No, sir.
That's why.
Sir, why have you written by theorem 14c? What's that?
Theorem 14c state that if there are the two solutions, their linear combination is also the solution. But it theorem 15 guaranteed that it is a general solution, depending that y1 and y2 must be the Li. If the y1 and y2 are LD, then also the c1 y1 plus c2 y2 will be the solution of the given equation. But in that case, we will not call that as a general solution. That is just a solution. In previous class, I have told you, no, if we have the equation y double dash plus y is equal to 0, so
Yes.
y1 is equal to sin x. Let us assume y2 is equal to 2 sin x. Then c1 y1 plus c2 y2 is also the solution, but not solution, but not general solution, but not general solution. But when we have the y1 is equal to sin x and y1 and y2 is equal to cos x, y2 is equal to cos x, then c1 y1 plus c2 y2 is a solution, and by the theorem 15, solution and also general solution, also general solution. That is the basic difference. In both case, by the theorem 14c, we have the solution. Linear combination is the solution. Clear?
Yes, sir.
Now
Sir,
we
so,
yes.
sir, so theorem 14c is valid for non-linear equations also, differential equations.
Non-linear.
Sir,
Yes,
theorem
it will
14.
be valid.
Okay.
It will be valid if it is the homogeneous.
Yes, sir. Okay, sir.
because whatever the extra constant, that all will go in zero.
Okay, sir.
Use of known solution. Now we are moving to the section 16. It is very important section. So now we are moving to the section 16. Use of known solution to find the another solution. We know that for writing the general solution, always we require the y1 and y2. So by inspection, by judgment, we can determine one solution easily. Now the question arises: can we, if one solution is known, can we derive another solution, which should be which should be linearly independent, so that you can write the general solution? So let homogeneous and linear second order differential equation is the y double dash plus px y dash plus qx y is equal to 0. And you assume that let y1 is known to you, y1 be the known solution of the first. So now we have to determine the another solution. So we try to determine another solution y2. So y1 is be the non-zero known solution. It should be the non-zero known solution, because we are always interested for the non-trivial solution. Trivial solution is always true, right? We are interested only for the non-trivial solution. So we assume that y1 is the non-zero solution. So you know that so what is the idea behind to find the another solution? So if I am saying that y1 is known, if I am saying that y1 is known, so n- just now I have told you constant multiple of solution is also solution, is also solution of first. Constant multiple of solution is also the solution. So we can say let it is the y2. But what we want? We want the linearly independent solution. Linearly independent solution like this we cannot write, because the constant if another solution is the constant multiple of the one solution, then they are the linearly dependent. But we are interested for the li solution, another li solution. So to get that, from here we will write that let y2 is equal to v into y1, where v is function of x, where v is the function of x. From here we are taking the inspiration to derive the another solution. So here we are writing the y2 is equal to v y2 is equal to v of y1. So y2 dash will come v dash, because v is also the function of x, v dash y1 plus y1 v y1 dash. Then y2 double dash will be the v double dash y1 plus v dash y1 dash plus v dash y1 dash plus v y1 double dash. Now we are saying that this is the solution of the given equation. Y2 is the solution of the given equation, right? We are claiming that y2 is equal to v of y1, and that is the solution of the given equation. So when it is the solution of the given equation, it must satisfy the given equation. Means y2 double dash plus px y2 dash plus qx y2 is equal to 0. If I am saying that let y is equal to vy1 is where this is solution of the given equation 1. So what is the value of the y2? Y2 is v double dash y1 plus 2v dash y1 dash plus v y1 double dash. That is the y2 plus px. What is the y2 dash? V dash y1 plus v y1 dash plus qx y y2. So v y1 is equal to 0. So when we collect the coefficient of v, so from the first bracket, here we have the y1 double dash. From the second bracket, we have px y1 dash, and from the third bracket, we have the qx y1 plus, if you collect the coefficient of v dash, so it will become 2y1 dash, from here 2y1 dash, and plus px y1 plus v double dash, right? So from here we have computed this. Now from v double dash, we have the y1 is equal to 0. Now what is the y1? Y1 is known solution, of first. If it is a known solution of the first, what will be the value of this? Its value will be the 0, right? So it will give you v dash 2y dash plus, or y1 dash px y1 plus v double dash y1 is equal to 0. So this will become 0. So here we have only this much. So here we have the another equation. So here we have computed, right? So here we have computed the v dash into 2 y1 dash plus p y1 plus v double dash y1 is equal to 0. So now we separate the variable. So when we separate the variable, here we have the y double dash upon v dash is equal to minus 2y1 dash upon y1 minus p. P is nothing, that is the function of the x. P is the function of x. So here v double dash upon now you have separated. So when you integrate, right, with respect to x, when you integrate with respect to x, so what you will get? You will get the log of the v dash minus 2 into log of y1 minus integral of the p dx. So from here v dash will be, the e to power minus 2 log y1 e to power minus integral of the p dx, and that can be written as 1 upon y1 square e to power minus integral p dx. So what is the value of the v? Just you integrate on both sides with respect to x. So v will come integral 1 upon y1 square e to power minus integral p dx with respect to dx. So that is the formula, right, with which you can determine the second linearly independent solution. Why? V2 is equal to what? V into y1. Y1 is known. And this you have computed. Now the question arises. Now this y1 and y2 must be the li. Then only you can write the general solution. So now we have to show only the y1 and y2 are linearly independent solution. So linearly independent solution. So what we compute? We compute the W, Wronskian of the y1 and y2. Y2 is what? V of y1. So what is the Wronskian? Y1, y2, y1 dash, y2 dash, and y2 is what? V of y1, and y2 dash we have already computed, v y1 dash plus v dash y1. So here we multiply. So here you first we will get v y1 dash v dash y1 square minus v y1 dash, right? So what is the advantage? Here you can cancel this. So you will get the v dash y1 square, And what is the V dash? V dash is this thing. V dash is equal to 1 upon y1 square e to power minus integral p dx. So when we put the value of V dash 1 upon y1 square e to power minus integral p dx into y1 square. So now y1 square and y1 square will cancel out. So here we have the e to power minus integral p dx. So you know that exponential function never zero, right? Exponential function will never zero. So never zero, not vanishes. So when not vanishes, you can say that y1 and y2 are li. If w is not equal to 0, right? So it will be the li. Clear? Here it is it is not equal to 0 implies y1 and y2 are li. When li, so you can write that c1 y1 plus c2 y2 is general solution. Then you can write its general solution. So that is the way to determine the second linearly independent solution if one solution is known to you. That is another matter how you know that the first solution. But if you know the solution, then second linearly independent solution you can determine by the section 16. Now let us start the question over this. Any doubt in this part in understanding how we have computed the second linearly independent solution? Anything, any concept you want to ask? Great. So verify that y1 is equal to x square is one solution of the equation x square y double dash plus xy dash minus 4y is equal to 0. Find y2 and the general solution. So in this case, first we have to check whether the given equation is linearly independent or means given equation is linear equation or not. Because whatever the theory we are giving here, that is true for the right, that is true for the linear equation. So first we have to check before proceeding. First we have to check that whether the given equation is the linear equation or not. Clear? So given equation is what? X square y double dash plus x y dash plus minus 4y is equal to 0. So first we have to write in the standard form. So here we have the x square y double dash plus x y dash minus 4y is equal to 0. Yes. Now it can be written as y double dash plus 1 upon x y dash minus 4 upon x square y is equal to 0. It means this is what? This is the px function of x, and this is what? This is the qx function of x. So here we can say that it is the linear equation. Now let y1 is equal to x square, known solution, known. Okay, first we have to verify that it is the solution. So y1 is equal to x square. So y1 dash is equal to 2x and y1 double dash is equal to 2. So when we put in the given equation, here you will get the 2, right? In this equation when we will put, so 2 plus 1 upon x into 2x minus, right, 4 upon x square into x square. So x square cancel out, x cancel out, and 2 plus 2 minus 4, that is the 0. That is the 0. So it means it satisfies the given equation. Clear? Now we have to determine the second solution. So here we know that by the by section 16. By section 16, v is equal to what? Integral 1 upon y1 square e to power minus p dx dx. So it will come 1 upon y1 square means y1 is what? X square. So x square whole square e to power minus. Now p is what? P in the standard form we have to check the p, right? In the standard form we have to check p. So 1 upon x. So here integral 1 upon x into dx into dx. So this will come integral 1 upon x to power 4 and e to power minus log x into dx. So that is the integral 1 upon x to power 4 into 1 upon x into dx. So it will become the x to power 5 integral x to power minus 5 into dx, and its integration will be x to power minus 4 upon minus 4. So what is the y2? It is the value of the v. So y2 will be v into y1. So minus x to power x to power minus x to power minus 4 upon 4, that is your v into y1, that is your x square. So this will give you minus 1 upon 4 x to power minus 2. So as you know, the constant multiple of the solution is the solution. So if you divide by the minus 1 by 4, that will also be the solution. So y2 will be the x to power minus 2. So the general solution, right? General solution. So you can say y2 is another linearly independent solution. Now here need not to check because we have computed from the section 16. In that we have already checked. So just by writing the section 16, now you have not to check whether the y2 and y1 are linearly independent or not. So general solution will become yx is equal to c1 y1 plus c2 y2. So it will become the c1 x square plus c2 x to power minus 2. That is your general solution. So
Sir,
from the, yes,
so while integrating for v, why don't we write constant?
if you write the constant, that will come also in this only.
I mean, we wrote na, okay, v is minus x to power minus 4 by 4 plus c. Why don't we write plus c there? Constant of
Here
integration.
you are writing na, here.
Ah, here, why don't we
So
write?
actually when we write na here, see, by chance you are writing, here you are writing, right? So it will come the plus c x square, right? For a moment you assume that it will come plus c x square. So when we add, it will give you c1 x square plus c2 x minus 2 plus c1 x square. So ultimately c1 c2 and this will give you another one more constant. So generally we do not write. Already we will get this solution only. C means as a y1 y2 we will get this only. Clear?
Okay, sir.
Sir,
Means
but
if you are
y2
writing there is no harm. If you are writing there is no harm, but ultimately in the general solution you will get the two arbitrary constants only. Clear?
Yes, sir.
Now this we have computed the general solution. Let us have another question. the equation 1 minus x square y double dash minus 2x y dash plus 2y is equal to 0 is the special case of the Legendre equation. Legendre equation is one chapter in your syllabus, right? So later on we will deal in detail, but here we are just dealing one special case of the Legendre equation by taking p is equal to 1. This is the standard Legendre equation 1 minus x square y double dash minus 2x y dash plus p into p plus 1 y is equal to 0 corresponding to p is equal to 1. It has y1 is equal to x. It has y is equal to x as a obvious solution. Find the general solution. Means we have the given differential equation is this. One solution is known. You have to determine the another solution. So in this case, so when we are claiming that it in one solution is known, so need not to check again. If they are asking you check, then it's okay. Otherwise, need not to check. So what is the given equation? 1 minus x square y double dash minus 2xy uh, 2xy dash plus 2y is equal to 0. So it can be written in the standard form y double dash minus 2x upon 1 minus x square y dash plus 2 upon 1 minus x square y is equal to 0. So this we can write in the standard form. So here px will be the what? Px is equal to minus 2x upon 1 minus x square, and qx is what? Qx is 2 upon 1 minus x square. Because in the formula we require the standard p. So here we have the second order linearly means second order linear equation. Now y1 is equal to x is known solution. It is given to you is the known solution. So now we have to determine the second linearly independent solution. So by section 16, y2 is equal to v y1, where v is what? Integral 1 upon y1 square e to power minus integral p dx into dx. So v is equal to what? V is equal to integral 1 upon y1 square, that is the x square, e to power minus now integral minus 2x upon 1 minus x square into dx, that is your p. So this will come integral 1 upon x square, and here we have the e to power minus log of 1 minus x square, 1 minus x square into dx. So this can be written as 1 upon x square into 1 upon 1 minus x square into dx. So here this can be written as integral 1 upon x square plus 1 upon 1 minus x square. If you take the partial fraction, so here it will come the 1 upon x square plus 1 upon 1 minus x square into dx. So if you integrate, so it will give you minus 1 upon x plus half log of x plus 1 upon x minus 1. So what is the y2? Y2 is equal to v of y1. So it will come minus, this is the v, so minus 1 upon x plus 1 by 2 log of x plus 1 upon x minus 1 into x. So this will give you this x and this x cancel out, so it will give you x by 2 log of x plus 1 upon x minus 1 minus 1, that is your y2. So when it is the y2, So what you know, what is the general solution? So general solution will be general solution if y1 and y2 are known. So general solution will be the c1 yx is equal to c1 y1 plus c2 y2. So c1 x plus c2 into x by 2 log of x plus 1 upon x minus 1 minus 1. That is your general solution.
Excuse me, sir.
Yes.
So when we integrate v, so why don't we
Huh?
put the integration constant?
Actually, here also the same thing, whatever just in previous question I have explained. If you add the c, just to easy the calculation part, nothing else, right? So as you add the c here, so here you will get the c, right? So here you will get the cx. So here you will get the cx. So ultimately you will get the c1 plus c2 x plus c2 x by 2 log of x1 plus 1 upon x1 minus 1. That we write. And c1 plus c2 you assume let it is the c3x plus c2 x by 2 log of x plus 1 upon x minus 1. This one. The same thing will come.
Okay.
So whatever that extra constant, and that will come in the first solution. That's why we, just to ease the computation, we avoid here there to write the constant of integration. Let us have another problem. Solve y double dash minus x upon x minus 1 y dash plus 1 upon x minus 1 is equal to 0. So in this case, here we have the equation y double dash minus x upon x minus 1 y dash plus 1 upon x minus 1 y is equal to 0. So px is what? Px is minus x upon x minus 1, and qx is 1 upon x minus 1. So in this case, I have told you in previous classes that how to recognize which one is the solution. When I have started the second order differential equation. So this is the formula, right? If we have the 1 plus p plus q is equal to 0, then y is equal to e to power x will be the solution. 1 minus p plus q is equal to 0, then y is equal to e to power minus x is the solution. A square plus p a plus q is equal to 0, then y is equal to a e to power ax will be the solution. P plus qx is equal to 0, y is equal to x is the solution. 2 plus 2px plus qx square is equal to 0, y is equal to x square is the solution. M into m minus 1 plus pmx plus qx square is equal to 0, then y is equal to x to power m is equal to the solution. So in this case, when we have this, so you can see that which condition it is satisfying. P plus qx, p plus qx is equal to 0, right? X upon, or you can say x upon x minus 1 plus x into 1 upon x minus 1, that is the 0. So this implies y is equal to x is solution of first. Let's say it is the first, so solution of the first. So we say let this is the y1 or known solution. So known solution. So second second linearly independent solution by section 16. By section 16, it will be the y2 is equal to v of y1, where v is what? Integral 1 upon y1 square e to power minus integral p dx into dx. So v is what? Integral 1 upon x whole square e to power minus and p is what? P is the minus x upon x minus 1. So integral minus x upon x minus 1 into dx into dx. So that is our v. So that can be written as integral 1 upon x square and e to power, this can be written as x upon x minus 1. So it is x
So we
minus
can
1
do
or x.
plus minus 1 in the numerator.
Hmm. So it will be the integral x minus 1 upon x minus 1 plus 1, this one, into dx into dx. So this will come 1 upon x square. Now e to power integral dx plus 1 upon x minus 1 dx into dx. So that is the 1 upon x square. So e to power x plus log of x minus 1, and here we have the dx. So what will come? It will be the 1 upon x square and 1 upon not 1 x minus 1.
Into x minus 1.
So it will be above x
नहीं,
plus.
एक मिनट, I think
Yes, sir.
Sir, it will be e raised to x into x minus 1.
I think we have uh,
Sir,
uh,
it will come e raised to x upon x integration.
I think in the question, I think I have to verify from the book. I think in the question here we have the plus.
No, it's 7A question is correct.
हाँ जरा if you have the book, then please check.
It's x minus 1, sir, in denominator.
In the book, x minus 1 only.
Yes, sir.
Sir, the integration is coming, sir, e raised to x upon x.
Sir, you can check your notes solution. That will.
Actually, so it is coming na x square into x minus 1 e to power x into dx. This is coming na, I think.
Sir, so if you take 1 upon x square inside, it will be 1 upon x minus 1 upon x square. So, sir, its integration will be e raised to x upon x.
Acha, that we can do. So it is the x minus 1 upon x square e to power x into dx. So its integration is the e to power x by parts. If you do the integration of this, then this will be the second one will cancel out. So it will come the e to power x upon x, right? So that is the v. So what is the y2? Y2 will be the v into y1. So e to power x upon x into x. So it will cancel out. So it will come only the e to power x. So the general solution will be the y is equal to c1 y1 plus c2 y2. That is the c1 x plus c2 e to power x. That is the general solution. So, so in next class we will start the new
Sir, we could
section.
do both the solutions using the hint.
We will
Sir,
use we can.
uh, sir, we can do both the solutions using the hint equations that you had given us.
Ha ha.
That way
1
we
plus
would
p
all.
plus q. All the equation depending over the what is the value of the p and q. Depending over the what is the value of the p and q, you can use any one. So I actually here also I have done the same mistake. Question is 1 upon means in the denominator we have the x minus 1, but in writing the solution I have taken the x plus 1. So we have the different answer. Some mistake, I think in here we have some mistake. So I have to check. It should be the minus 1. So final answer is coming the same thing, but I have done some calculation mistake here. But whatever I have shown you, that is the correct one. So that is the solution. So time is over. So I will continue in the next class. So any doubt? In next class, I will start. I will one question is remain from this section. Then I will start the new section. That is the easy one. Any doubt?